Have you ever stared at a candle flame and wondered, how does it know which way is up? It's almost eerie, isn't it? Tilt the candle and the flame tilts back. Blow gently from the side and it leans away. But the moment the air calms down, it straightens itself again, as if pulled by some invisible string toward the ceiling. And here's an even stranger twist. Take that same candle into space where there's no up or down, and the flame suddenly turns into a floating blue sphere like a tiny star. So what's going on? Why does fire seem to know where to go, and why does it act so differently when gravity disappears? To answer that, we need to step into the invisible world that surrounds every flame. When you look at a flame, what you're actually seeing is a region of hot gases glowing from heat and chemical reactions. The fire isn't a solid object, it's a moving process. But this process doesn't happen in isolation. It lives inside a constant conversation with the air around it. In our everyday world on Earth, gravity is always in that conversation, pulling heavier things downward and letting lighter things rise. You've probably noticed that hot air balloons go up. That's because hot air is less dense than cold air. It expands, the molecules spread out, and gravity's pull is weaker on it compared to denser cold air. A flame is like a hot air balloon factory running non-stop. It heats the surrounding air, which expands and rises. As the hot air leaves, cooler air from below rushes in to replace it, bringing fresh oxygen to feed the fire. This creates an upward current, a kind of invisible conveyor belt that constantly pulls the flame toward the sky. This is the first part of the answer. A flame doesn't choose to point upward. It's sculpted by the movement of air caused by heat and gravity working together. But let's make that picture even clearer. Imagine you're in a swimming pool holding a colored air bubble underwater. The bubble always races upward to the surface no matter which way you tilt your hand. That's because the water around it is denser and the lighter air inside the bubble is pushed up by buoyancy. In air, the same principle happens, but it's much weaker because air is already less dense than water, but it's still enough to make hot, light gases from the flame rise. The flame just rides that rising flow. But here's where the analogy gets more interesting. In water, if you were in zero gravity, say on the International Space Station, your air bubble wouldn't rise. It would just float in place because there's no up for it to move toward. The same thing happens to a flame in space. Without gravity, there's no buoyancy, no rising current, so the flame stops being a teardrop shape and turns into a perfect sphere. It's still burning, but the hot gases just sit there, slowly diffusing outward. On Earth, we're so used to seeing flames dance upward that it feels almost like a law of nature. In reality, it's just one outcome of the constant tug of war between heat, air, and gravity. The heat makes the air lighter, gravity pulls the cooler air down and lets the hot air escape upward, and the flame's shape is the visual signature of that cycle. But wait, there's another hidden player in this game: oxygen supply. Fire needs oxygen to keep burning. On Earth, fresh oxygen naturally gets pulled in from below the flame by the rising currents of hot air leaving at the top. That's why a candle burns steadily without you needing to fan it. In space, with no up or down, oxygen doesn't flow in the same way. The flame has to rely on slow, random mixing of gases, something called diffusion. That's why flames in zero gravity are dimmer, smaller, and often burn cooler. Now let's zoom back to our candle here on Earth. When you blow on it from the side, you're forcing a much stronger current of air into that delicate balance. The hot gases are swept away, oxygen is blown off its usual path, and the flame bends dramatically. But the moment you stop, the buoyancy-driven current reasserts itself, and the flame straightens up again, following the invisible river of rising air. This explains another everyday observation: the flickering of a flame. When you see it dancing, you're watching tiny changes in those air currents, maybe from your own movements, maybe from the heat bouncing off nearby surfaces, or even from sound vibrations in the room. The flame is constantly responding to these shifts, reshaping itself dozens of times per second. There's a poetic beauty to this, because in a way, the flame is a map of the air it lives in. You could think of it like a windsock at an airport. It shows you the invisible wind, but on a much smaller and more sensitive scale. And this sensitivity is why, for thousands of years, humans have used flames as a tool for detecting things we couldn't otherwise see. Before we had advanced instruments, miners carried candles to check for dangerous gases in tunnels. A flame's behavior would change instantly if the oxygen level dropped or if flammable gases were present. So the flame's knowledge of where to go is really its ability to adapt instantly to the environment. gravity, airflow, and oxygen supply, without any brain, without any decision-making. It's pure physics, and this is where our aha moment hits. A flame is not a thing, it's a choreography. It's the visible result of heat changing the density of air, gravity sculpting the flow, and chemistry lighting the stage. Remove one of those elements and the dance changes entirely. This realization flips how we think about fire. We often imagine it as an object, a hot, wiggly blob that moves around. But it's more like a standing wave in a river, always in place but made of constantly moving water. The flame you see now is not the same flame you saw a second ago. It's a living pattern, rebuilt moment by moment from fresh air and new molecules of gas. And here's where things get even more fascinating. This pattern nature of flames is why engineers study them so closely in microgravity experiments on the ISS. Without gravity interfering, we can isolate other factors, like how fuel mixes with oxygen, and this leads to better designs for engines, safer fire suppression systems, and even more efficient stoves back on Earth. So the next time you light a candle, remember, it's not that the flame knows where up is, it's that the world around it, gravity, heat, and air, is constantly whispering directions. And the flame is just the perfect, ever-changing response to those whispers. This leads us to one of the most fascinating aspects of fire. It's a storyteller of its surroundings. Think about it. Every flicker, every lean, every change in brightness is a clue about what's happening in the invisible world of air. It's like a live visualizer for physics. When you watch a flame, you're essentially reading a constantly updated map of temperature differences, pressure gradients, and the dance of molecules all around you. And here's something that might surprise you. The shape of a flame is one of the simplest natural indicators of convection. Convection is just the movement of fluid, in this case air, caused by temperature differences. Hot air rises, cool air sinks, and the cycle continues. Without gravity, there's no up for the hot air to rise toward, and convection stops. But on Earth, convection is so reliable that it becomes a kind of silent sculptor, shaping the teardrop form of every candle flame you've ever seen. Once you start looking for convection, you see it everywhere. The way steam rises from your coffee, the way clouds form and shift, even the way your home warms up in winter. These are all convection stories. The flame just happens to be the most obvious and mesmerizing one because it glows while it's telling you its tale. But there's also an even deeper reason why flames act the way they do: chemistry and the way oxygen interacts with fuel. Imagine the flame as a tiny engine. It pulls in oxygen, mixes it with fuel vapor, and ignites it. On Earth, convection brings in fresh oxygen efficiently from below. This is why the base of a candle flame is blue, the hottest part where oxygen is plentiful and combustion is most complete. The upper part of the flame glows yellow because the oxygen is running out, and tiny bits of carbon, called soot particles, heat up and emit light before they burn away. In space, with no convection, oxygen has to reach the flame only through slow diffusion, molecule by molecule. This makes the flame smaller, cooler, and bluer because combustion is more even but less intense. That's why scientists are so interested in studying flames in microgravity. It reveals aspects of combustion that are hidden on Earth. This research has real-world applications. Understanding combustion without gravity helps us design cleaner engines, reduce pollutants, and improve fire safety systems. For example, on Earth, flames often go out when deprived of oxygen because convection can't sustain them. But in space, flames can keep smoldering longer in low oxygen conditions because the heat isn't carried away as quickly, something that can be dangerous on spacecraft. So yes, learning why a flame knows which way to go can literally save lives. And once you grasp that a flame's shape isn't magic but a product of physics, you start to see connections everywhere. The same principles explain why smoke rises in a column before spreading out, why the sun's surface boils with loops of plasma, and even why weather systems form on Earth. In fact, you can think of Earth's atmosphere as one gigantic slow-motion flame, heated by the sun, shaped by gravity, and constantly moving as warm air rises and cool air sinks. Here's another fun twist. Flames can lie about which way is up if you cheat the air currents. In a strong horizontal wind, the flame points sideways, not because gravity has changed, but because the wind's force is overpowering the gentle upward push of convection. In a vacuum, of course, flames can't exist at all. There's no air, no oxygen, no fuel mixing. That's why space is dark despite being full of potential fuels like dust and gas. Without the right conditions for convection and combustion, nothing burns in the way we're used to. So next time you light a candle, take a moment to really look at it. The flame is not just burning, it's negotiating with its environment in real time. It's responding to every breeze, every tiny shift in air temperature, every change in oxygen concentration. What you're seeing is a natural feedback loop. Heat changes air, air changes flame, flame changes heat. It's an elegant self-sustaining cycle, and once you notice it, it's hard to unsee. There's a certain magic in knowing that something so familiar is shaped by such profound forces. You can hold it in your hand, yet the rules governing it are the same ones that drive storms, heat planets, and shape stars. And here's the beautiful part. You didn't need a physics degree to understand it, just curiosity and a good analogy or two. That's the real superpower of science, turning invisible patterns into stories we can all see and feel. If you've made it this far, you've just unlocked a new lens on the world. Every time you see fire now, you'll remember the invisible currents guiding it, the constant pull of gravity shaping it, and the delicate dance of chemistry sustaining it. And who knows, maybe next time you'll notice the same principles in your coffee steam, in a summer breeze, or in the clouds drifting overhead. Because once you start to see how it actually works, you can't stop seeing it everywhere. And if you enjoyed this journey into the hidden life of a flame, imagine how many more everyday wonders are just waiting to be decoded. That's what we do here. Take the mysteries of the world and hand you the key to understanding them. So, if you want to keep unlocking the secrets behind the ordinary and seeing the extraordinary in everything, like this video, share it with someone who still thinks fire chooses where to go and subscribe to how it actually works. Your curiosity is the fuel, and we've got an endless supply of sparks.